Hello friends, good morning, wherever you are. This is IBM with yet another episode of Learning Physics with IBM. And today I want us to take the concepts of ideal gases further. You can call this ideal gases part 2, or it's a continuation of ideal gases. And I hope today we shall come to a conclusion of this part of the topic. So just to review, or just to remind ourselves about what we saw in the previous lesson, let's have a simple lesson review. I said last time that in this unit of ideal gases, we shall look at the equation of state, the kinetic theory of gases, the pressure of the gas, and the kinetic energy of a molecule. And if I'm not mistaken, I think we talked about the mole. In the previous unit, we talked about the mole. And by now you should have understood what we mean by a mole. We also said the mole is the amount of substance which contains as many elementary entities as there are atoms in 12 grams of carbon-12. So in the previous unit the previous lesson, we understood what we mean by a mole. We went ahead and talked about another concept, that is Avogadro's constant. We talked about Avogadro's number or Avogadro's constant. What is the spelling of Avogadro? Avogadro. I think it's A-D-R. Talked about the Avogadro's number or the Avogadro's constant, which is represented by Na. We said this is the number of atoms in 12 grams of carbon-12, as simple as that. We also talked about the molar mass. We talked about the molar mass, which I normally represent by m subscript small r, as the mass of 1 mole of a substance, whose unit was the gram per mole. We must have done a few examples. Then we talked about the equation of state. But before talking about the equation of state, we talked about the three properties which we called the macroscopic properties. And the macroscopic properties include the volume, they include temperature, and pressure. And I say these three are said to be macroscopic because they can easily be observed and measured using some maybe particular instrument. So we studied the relationship between these properties, and we say the relationships actually summarized into laws, where the first law was so much interested in finding the relationship between volume and pressure, where we saw that the pressure or the volume was inversely proportional to pressure, and we say this was Boyle's law. We also saw the second relationship, which was interested in temperature and volume at constant pressure, which was Charles's law, in memory of Jacques Charles. And according to Charles, the volume was directly proportional to temperature if the pressure was kept constant. Remember, T was thermodynamic temperature. And our third law, which was Gay-Lussacre's law, or sometimes simply called the pressure law, this was when the volume was kept constant, and we saw that the pressure was actually directly proportional to temperature. So when we combine these three equations, we came up with a simple equation that the pressure times the volume were directly proportional to temperature, which meant that PV over T was equal to a constant. So we were able to come up with such an expression. We established our constant, and we said for n moles of a gas, then the pressure PV was equal to N RT, and we called this one the equation of state. P was pressure of the gas, V was the volume of the gas, N was the number of moles of the gas, R was called the molar gas constant, and T was thermodynamic temperature. So we must now be familiar with this expression. We also try to relate this to another expression by removing R, where we said a new quantity had to be redefined, and that was K. we saw that since the number of moles N was equal to the mass divided by the molar mass, which is the same as the number of particles divided by Avogadro's number, we realized that N, capital N, could be defined as N times Avogadro's number. I don't always like to write N subscript small a. So we could now also, or alternatively, we could replace N with the simple N over NA. So this meant that PV would be equal to, where there is N, I can put capital N over Avogadro's number, then times R times T. And we saw that R divided by NA was actually equal to a constant K. The constant K was equal to R divided by NA. And we say that this constant K is actually called Stefan Boltzmann's constant, which is given a value approximately 1.38 times 10 power negative 23 joules per Kelvin. Joules per Kelvin. So precisely we could write the expression PV to be equal to NKT as another way of writing the ideal gas equation. I mentioned in the previous lesson that you must now make yourself comfortable with this expression. We say that this is the defining equation of what we call the ideal gas. We say that an ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. So all we need is to define the quantities in the equation PV is equal to nRT. But I said that the above laws, the laws of Boyle, Charles, and pressure, were not actually laws, simply because they were only valid under specific conditions. They had their validity was actually restricted. We said they are accurate for real gases only if the pressure of the sample is not too great. And if the gas is well above the liquefaction temperature, such laws could be approximately be obeyed or could be valid. Unfortunately, we could not have such a gas existing as a gas when the pressure is not too great and yet is at a temperature above liquefaction. Therefore, we say that such a gas is said to be ideal. It's actually an ideal gas. So we said an ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. So the gas is just ideal. I explained the meaning of the word ideal in the previous lesson. So we did several examples, and I say those examples should make you confident. They should make you confident with the concepts of using the equation PV is equal to nRT. So you must have gone through those examples and attempted the self-check. Okay, let's now proceed. Today I want us to continue and finish ideal gases. So next we should be looking at the kinetic theory of gases. We should be looking at the kinetic theory of gases. So what do we mean by kinetic theory? Earlier on, we have talked about the macroscopic properties of a gas. The pressure of a gas could be easily be measured. The temperature of a gas could easily be measured using a thermometer. And the volume of a gas could easily be measured. But how about the velocity, the mass of a molecule, or the kinetic energy of a molecule that makes up a gas? How possible is it to measure the mass of a molecule of a gas? How possible is it to measure the velocity of just a molecule of a gas? How possible is it to measure the kinetic energy of a molecule of a gas? Now, these concepts that I've been talking about, the mass of a gas, the velocity of a gas, and the kinetic energy of a gas are too small quantities atoms or molecules which make up a gas. These are very small quantities. Therefore, we cannot easily measure them or observe them. These ones we normally call them the microscopic properties of a gas. The mass of a gas. Talk about the mass of a gas. Talk about the velocity of a gas. Talk about the kinetic energy of a molecule. Actually, we can't talk about the mass of a gas in general, but we can talk about the mass of a molecule. We can talk about the velocity of a molecule which makes up a gas or which is part of the gas, or the kinetic energy of a molecule which is part of the gas. So these ones are going to be called microscopic properties. They are going to be called microscopic properties. So what we call the kinetic theory of matter. This is simply a statement of how we believe atoms and molecules, especially those in gases, behave and how it relates to the ways we have to look at things around us. So it is just a statement giving an explanation of how molecules or atoms that make up gases behave. This explanation also helps us to understand and to change the way we think about things around us. So the kinetic theory of gases is just a statement. Sometimes it is called the microscopic model of gases. Microscopic model of gases. So it is like a very good way to relate to the micro world, which is, of course, micro, we are referring to small realms, very small quantities. So in the kinetic theory is going to help us to link the micro world to the macro world. Remember, in the macro world, we talked about the macroscopic properties of a gas, such as the pressure of a gas, the temperature of the gas, and the volume of the gas. In the microscopic world, we are talking about very small realms. I'm mentioning the word realms. Realms. Very small realms. For example, the mass of a molecule of a gas, the velocity of a molecule or the speed of a molecule of a gas, and the kinetic energy of a molecule of a gas. If you recall from nuclear physics, we saw that the energies that were involved at nuclear level were extremely small, and even the masses were the mass defects were extremely small. That actually the unit kilogram for mass was too big because the realms we were talking about were very small at nuclear level. So similarly here in the micro world, the quantities, mass of a molecule or mass of an atom of a gas, its speed or its kinetic energy are very small quantities. But in the kinetic theory, we are going to be able to link the large quantities, which are the macroscopic properties of temperature, volume, and pressure, to the small quantities, that is the mass, velocity, and kinetic energy. To begin with, I think it is 1827 when the English botanist in the name of Robert Brown was trying to observe tiny pollen grains which were suspended underwater, which were suspended in water, and he was observing them under a microscope. This is the origin of the kinetic theory of gases. Sorry. So what did Robert Brown observe? In our next slide, I want us to talk about Brownian motion. What did Robert observe? Robert observed that the pollen grains, which were on the surface of water, were not actually stationary when viewed under a microscope. In fact, his observation showed that the pollen grains, we know pollen grains because we have studied some biology, those, I think they are the reproductive parts of a flower, I think. Those pollen grains which had fallen on water, which water was completely still, were seen to be moving in a jerky, zigzag, haphazard, random motion. So Robert Brown, the English botanist, observed that the pollen grains which were suspended in water, when viewed under a microscope, they were not actually stationary. Today, this movement of pollen grains was now termed as Brownian motion. But then, what is the significance or the essence of this motion? So, let's think of water being completely still. Then why do the pollen grains move haphazardly or randomly on the surface of water? Think of a situation where you pour water in a cup and then place pollen grains on the top, on the surface. Just get a flower and then just try to rub on the surface of that, they call it that is it I don't know how they call it biologically, but just get a flower and try to shake the flower on top of the water in a cup. If you were to view the pollen grains from the flower which has fallen on the water under the microscope, you'll be seeing them moving haphazard or in a zigzag fashion. This is what we call Brownian motion. What is the significance of this? What do we conclude from this motion? So we can make an assumption that the water molecules are in rapid random motion. Then it is easy to understand how pollen grains could be moving haphazard or in a zigzag fashion. This is simply because they bombard from all sides of the water molecules. They are always colliding with the water molecules. And because the water molecules, although the water is considered to be completely still, the water molecules themselves are in a continuous random motion. So we are saying the reason as to why, or the explanation we can give for the pollen grains always moving in a zigzag fashion, even when the water is completely still, is because the water molecules themselves are not actually still. Although we can't see them move, the water molecules themselves are not actually still. So, because the pollen grains can be seen under a microscope, we can see them changing direction, moving in a zigzag fashion, simply because they are actually continuously colliding. They are continuously being bombarded by the water molecules from all sides. So when a pollen grain X collides with a water molecule Y, it changes its direction. As it moves, it collides with another water molecule, it keeps changing the direction. So this is evidence that the water molecules themselves are moving randomly in different directions. So Robert Brownie's experiment with pollen grains could be reproduced in the laboratory by simply observing tiny soot particles in smoke. For those of you who live in villages like me, if you live near a dusty place, just look at the ventilators now. You are going to see that if you look at the ventilators on your in the direction of the sun now, you must be seeing dust particles through the ventilators, and you must be seeing them moving randomly in any different direction. The same thing could happen with the soot, tiny soot particles in smoke. If you flash light in smoke at night, for example, you are going to see dark soot particles moving in different directions. The question will be, why are these smoke particles moving haphazardly like this, or randomly like this, or in a zigzag fashion? So now we can explain this random motion, that the soot particles or the smoke particles or the tiny dust particles you see through the ventilators are actually continuously colliding with the air molecules, which move in different directions randomly. So the particles move in a zigzag manner, just like the pollen grains. So this one could easily be reproduced in the laboratory using tiny soot particles in smoke. We can observe Brownian motion. Therefore, we are saying that When pollen grains collide with the water molecules, they keep changing direction. That's why they are seen under a microscope to be moving in a zigzag fashion, because they are always bombarding with the air molecules from all sides. This is some evidence that the water molecules themselves are not completely still, even when you have water completely still in a cup. In a similar way, we can extend this to smoke particles. I have said when you observe tiny soot particles in smoke, you are going to notice that they are actually continuously changing direction. And the reason as to why they are continuously changing direction is because they are colliding with the air molecules. So we can't see the air molecules even if we are using a microscope. We may not see the water molecules even if we are using a microscope. But all we can see is that, all we can conclude is that the molecules are continuously moving in different directions. That's why the pollen grains which we can see move in a zigzag fashion. The soot particles which we can see move in a zigzag fashion. The dusty particles that you can see through your ventilator in the direction of the sun are moving in a zigzag fashion, simply because they are colliding with the air molecules. So this can easily be illustrated on this page. This could easily be illustrated here. So if we were to observe soot particles or smoke particles in what I called a smoke cell or a glass cell, of course it should be illuminated to make them visible, because the microscope relies on light. So there should be light, there should be an illumination on the glass cell so that the smoke particles can be made visible. So observation using the microscope will show that one particular particle X will keep moving in that zigzag fashion, as you can see. And the reason as to why it will be moving in this zigzag fashion, we have already explained it. It is continuously bombarding the air molecules inside the glass cell. These air molecules move randomly in any particular direction, giving the same motion to the soot particles. It is moving initially in this direction, it collides with a molecule somewhere there, it changes direction, it collides with another molecule, it changes direction, it collides with another molecule, it keeps changing direction, and so on and so forth. So the zigzag motion is as a result of colliding with air molecules which are moving randomly in any direction. Thus, it seems that molecules of both gases and liquids are in the rapid random motion which is required by this model. So Brownian motion gives us evidence of this continuous random motion of particles in liquids and gases. So when somebody talks about Brownian motion, he is actually referring to the random motion of molecules of liquids and gases. The continuous random motion of the particles, the atoms, the molecules in liquids and gases is what we call Brownian motion. The continuous random motion of particles in liquids and gases is what we call Brownian motion. So after Brownian motion, nearly a century later, Albert Einstein made a simple theoretical analysis of Brownian motion, and for the masses and distances moved by these suspended particles, such as the soot particles or the smoke particles, Albert Einstein was able to estimate that the typical diameter of an atom is approximately 10 power negative, I think it's negative 10 meters. And I think we established this in particle physics. Those of you who remember the scale of things. So Albert Einstein was just able to detect the mass of the suspended particles, and the distances they moved. And he was able to use these two to estimate the diameter of a typical atom, which was approximately 10 power negative 10 meters as the diameter of an atom. The way he did this is not part of this lesson. Okay, so having seen that, we can now come to a conclusion. Number one, the molecules of both gases and liquids are in the rapid random motion, which is required by the microscopic model. Number two, Brownian motion gives us evidence of the continuous random motion of particles in liquids and gases. And I said when somebody talks about Brownian motion, this person is referring to the continuous random motion of particles which make up liquids and gases. Number three. So I said nearly a century later, Albert Einstein made a theoretical analysis of Brownian motion, and for the masses and distances moved by the suspended particles, he was able to estimate the diameter of a typical atom to be of the order 10 power negative 10 meters. And I said we are now familiar with this quantity. It's not something we are seeing for the first time. Okay, so let's proceed. So there are a few points to note here. Number one, the obvious difference between a solid and a liquid is this one here. A solid has what we call rigidity. We call it rigidity even in IGCSE. However, the microscopic model explains this by suggesting that atoms are held in fixed positions by much stronger interatomic forces than in liquids or gases. Does it mean that Brownian motion cannot be extended to solids? Perhaps yes, because in solids, the atoms are held together by very strong interatomic forces. Unlike liquids and gases where molecules or atoms are free to move, those in solids are not actually free to move. They are arranged in regular patterns that we call the lattice. So this is because the molecules are arranged quite close together in a solid, whereas in gases and maybe perhaps liquids, there is a great deal of empty space. So in gases and liquids, the molecules are free to move. So atoms in solids, I think, can still move. But from IGCSE, we say their motion is restricted to vibration about their mean equilibrium position. They can still move, but they can't move from one point to another as solids, as atoms of liquids and gases. Their motion is restricted to only vibration about their equilibrium position. So in solids, motion is restricted to vibrations only about their mean position. So the kinetic energy of molecules which make up solids is as a result of their vibration only. But of course, the kinetic energy of molecules which make up the gas is due to their free random motion as explained by Brownian motion. The same thing happens with the liquids. So then what happens in the change of state? So atoms in solids can still move, but we are saying in solids, their motion is restricted to vibration about their mean equilibrium position. But then, in the change of state of a solid to a liquid, work must be done. Where is this work going to be done? The work is going to be done to break the bonds which keep these atoms close to each other or tightly fixed to each other. The work done to break these bonds, as we shall see later on, is going to be called the latent heat of fusion. In IGCSE, you talked about latent heat of fusion. You remember the word latent meant concealed. This heat is applied to a system, but this heat did not increase the temperature of the system. However, this heat was just used into breaking the bonds, or this energy was just used to break the bonds so that the atoms can move freely. So whenever there is a change of state, work must be done to break the rigid interatomic forces so that the atoms can move freely. We shall call this latent heat of fusion for a solid turning to a liquid. Remember the word latent heat. The word latent means concealed. We cannot physically see the effect of latent or the effect of the heat supplied. That's why it is called latent. The effect cannot physically be seen because it doesn't cause a change in temperature. The temperature remains constant. But heat is being supplied. Where is the heat going? We are going to see this later in details, that this heat simply goes into breaking the bonds. This heat simply goes into breaking the bonds. Okay, let's talk about the pressure of a gas. Pressure of a gas. Now that we have seen the kinetic theory of a gas, we have seen Brownian motion, and we have seen that molecules or atoms of a gas are in continuous random motion because they are always showing zigzag motion with pollen grains, that is for water, for a liquid, and with soot particles for air and dusty particles for air still. The dusty particles were in continuous random motion. So now, how does a gas exert pressure? We answered this question in IGCSE and we just want to answer it again. How does a gas exert pressure? An explanation of how a gas exerts pressure could be traced back by Robert Boyle in the 17th century, but then in greater details it was given by Daniel Bernoulli in the 18th century. Of course, Robert Boyle gave a simple explanation from his relationship between volume and pressure, where he had established that the volume of a fixed mass of a gas was inversely proportional to the pressure. But his explanation was not actually very convincing. But later in the 18th century, another scientist in the name of Daniel Bernoulli, Daniel Bernoulli gave a more detailed explanation of the pressure of the gas. Let's think of how a gas exerts pressure by looking at a simple diagram. Let's think of a simple container, and we think of just one atom in the container. How does, and here we have a gas, and we're just pulling out or thinking of one atom of a gas in the container out of the many which are in the container. Remember, the atoms or the molecules of the gas are in continuous random motion, moving about each other at a very great speed. So let's think of this atom colliding with the wall of the container. When this gas atom or molecule hits the wall of the container, what happens? Immediately it rebounds. This atom immediately rebounds. When it rebounds, what has happened? Let's say it has a mass m moving towards the container, therefore with a speed v, it is moving with a momentum, say mv. When this atom or molecule collides with the wall of the container, there is a change in momentum. Let's assume it maybe rebounds with a different speed, but the mass has not changed. Since it is in the opposite direction, then the new momentum is going to be m times u. So there has been a change in momentum. So the change in momentum could be maybe given by an expression which is now m into v plus u. Because of change in direction, this is plus. So what has happened? Since there is a change in momentum, remember the change in momentum is called an impulse. There is a change in momentum, the change in momentum is called an impulse. So, since there is a change in momentum, Over a given period of time of contact, then there is a force exerted on the wall of the container, because force is equal to the rate of change of momentum. Force is the rate of change of momentum. So when the gas molecule hits the wall of its containing vessel, it rebounds. There is a change in momentum of the molecules, and it experiences what we call an impulse. Impulse is simply change in momentum. Then remember Newton's third law, which in A level we shall just be writing N3. When I see N3, I know it is Newton's third law. By Newton's third law, because the molecule or the atom experiences a change in momentum, then by Newton's third law, the wall or the container, the containing vessel, also experiences an impulse. By Newton's third law, the wall of the vessel or of the container will also experience an impulse. But remember, there are thousands of molecules. There are thousands of molecules, meaning that there are several or there are many collisions per unit time of all these molecules with a different wall or with a wall, and all these collisions and their associated impulses will average out to give a constant force on the wall. Because there are thousands of molecules, each colliding with the wall of the container, all these collisions with the associated impulses will give an average force on the wall of the container. And then you remember, pressure is defined as the force acting normally per unit area. This average force on the wall of the container per unit area of the container will therefore be the pressure of the gas on the wall of the container. I will repeat this. The kinetic theory has already suggested that the molecules which make up a gas are in a continuous random motion. They are moving about each other at a great constant speed. When we think of a single molecule hitting the wall of the containing vessel, it rebounds. There is a change in momentum of this molecule. In other words, the molecule experiences a change in momentum. Therefore, it experiences what we call an impulse. Then, remember, by Newton's third law, the wall also experiences an equal but opposite impulse. But remember also, force is equal to the rate of change of momentum. In other words, impulse per unit time. And there are several molecules within the gas, meaning that there are many collisions per unit time of all these molecules with the wall, and all these collisions together with their associated impulses will average out to give a constant force on the wall, because force is the rate of change of momentum. And from pressure is force per unit area or force acting normally per unit area, the force exerted on the wall by all these molecules per unit area of the wall is going to be the pressure of the gas on the wall. So that is how the molecule, that is how the gas exerts pressure. Let's have a simple review of this. Number one, we say the gas consists of atoms or molecules randomly moving about at a great constant average speed. That is according to the kinetic theory of matter. Number two, when a gas molecule hits the wall of its containing vessel, it rebounds. If it rebounds, there is a change in momentum of the molecule and it experiences an impulse. So the gas molecule experiences an impulse when it collides with the wall of the containing vessel. Then by Newton's third law, the wall of the vessel also experiences an equal but opposite impulse, which you wrongly say actions and reactions are equal but opposite. Number four, there are several collisions per unit time of molecules with the wall, and all these collisions and associated impulses average out to give a constant force on the wall. And lastly, this force per unit area of the wall is what we call the pressure of the gas. So from today onwards, you should be able to account for how a gas exerts pressure on the walls of its containing vessel. you should be able to account for how a gas exerts pressure on the walls of its containing vessel. You should be able to explain this qualitatively. Okay, we are still continuing with the kinetic theory of gases, and we are going to be specifically concentrating on the ideal gas. Kinetic theory of gases. What assumptions do we make every time we look at the kinetic theory? What can we consider about the ideal gas? Remember, we said an ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. And I said in practice we don't have a gas which is ideal. Think of a gas existing as a gas at a low pressure or at a pressure which is not very great, but then when it is at a temperature at which the gas is supposed to be a liquid. It's quite abstract to understand, but it is easy to internalize. So, which assumptions do we take every time we apply the kinetic theory on an ideal gas? Number one, we always assume that all molecules of an ideal gas behave as identical, they are perfectly identical, they are extremely hard that even when they collide with the walls, nothing happens to them. They are perfectly elastic spheres. So we are always going to assume that all molecules behave as identical, hard, perfectly elastic spheres. Number two, we are also going to assume that, remember, these are just assumptions. The volume of the molecules is going to be negligible compared with the volume of the containing vessel. This is an obvious assumption we always talk about because we know that for a gas, any number of molecules available in a gas will spread out to fill up the whole containing vessel. Therefore, it is possible that the total volume of the molecules compared to the volume of the containing vessel is very, very small and negligible. By the way, if you use gas for cooking, you may even never know that the quantity of gas remaining is very small unless you have a pressure gauge. But all of a sudden you are cooking and you see that the gas flame goes off or the flame goes off because the gas has got exhausted. Even the smallest quantity of gas remaining always fills up the whole container. But think of if you were to bring those molecules together and add up their volume and compare with the volume of the container itself, you will notice that the total volume of the molecules of a gas is always far, far, far smaller than the volume of the container itself. Only that the molecules spread apart to fill up the whole containing vessel. So we are going to always assume that the volume of the molecules themselves is negligible compared with the volume of the containing vessel. Number three, there are no forces of attraction or repulsion between molecules. In other words, the intermolecular forces of attraction or repulsion between the molecules of an ideal gas are negligible. Later on, we are going to see that for an ideal gas, because the intermolecular forces are negligible, the potential energy contribution of the molecules is zero because it also relies on these forces. So for an ideal gas, we shall see that the intermolecular forces are actually negligible. Therefore, the potential energy of the molecules is also negligible. We shall see that under thermodynamics. So, when somebody talks about an ideal gas, remember it means or is referring to that gas where the forces of attraction or repulsion are negligible. In fact, the molecules are infinitely far from each other that one molecule does not experience a force due to the neighboring molecule. That's why we say the intermolecular forces are negligible. Unlike the real gas, where there is at least some weak force of attraction between the molecules or repulsion between the molecules, for an ideal gas, the molecules are considered to be infinitely far from each other. that the forces of attraction or repulsion cannot be experienced, or they are not appreciable. Okay, number 4. We also assume that there is always a large number of molecules which are all moving randomly. Therefore, an average behavior will always be considered. By the way, whenever we talk about an ideal gas, we shall always just be referring to an average behavior of all the molecules. We cannot talk about just one molecule. We cannot just look at the behavior of one molecule. We can't find the temperature, the mass of a single molecule. We can't find the speed of a single molecule. We cannot easily find the kinetic energy of a single molecule. But all we shall be looking at is the average behavior of all the molecules. Therefore, whenever we have an ideal gas, we always assume that we have a large number of molecules, and an average behavior will always be considered. Number 5. Assumption number 5. We also assume that the duration of collisions is negligible. That is, the time of contact, maybe between the walls of the container with the molecules or between the molecules themselves, is very, very small and negligible. Every time we deal with ideal gases, this is what we assume. We assume that when molecules collide, their duration is very small and negligible. And if their duration is very small and negligible, it means that even the force they exert, because the force is equal to the rate of change of momentum, because this is too small, it means that the force is relatively going to be large. So the duration of collisions is negligible. So these 5 are what we call the assumptions of the kinetic theory of ideal gases. Why do we talk about these assumptions? Because we shall need them in deriving equations relating to pressure. Remember, we said in kinetic theory, we link the microscopic world to the macroscopic world. In other words, we link concepts of mass, of kinetic energy of molecules, velocity or speed of molecules. We link these to the macroscopic properties such as volume, pressure, and temperature. So we shall need these assumptions for an ideal gas to be able to link the microscopic world to the macroscopic world, as we are going to see. I hope these assumptions are very direct. They are home and dry to you. So let's now start using the assumptions. We are going to be able to derive the equation pressure is equal to a third. Pressure is equal to a third rho. This is going to be read as mean square speed. Mean referring to average. So we are going to derive this expression. Now, in this is for an ideal gas. So this is a macroscopic property, but this one is a microscopic property. So this expression links the macroscopic world to the microscopic world. So we are going to be able to derive this expression. Okay, so let's try to see the link between pressure and the mean speed of the particle. We are going to see this in details. We shall explain these symbols later on in details. Now I have considered, we are going to consider a large number n. Consider a large number n, capital, I will call this capital N, of molecules of a gas. Let each molecule have a mass small m. Consider a large number n of molecules of a gas. Let each molecule have a mass m. Let them be contained in such a cubical container as this one drawn here, whose sides have length L. Remember, it is cubical, meaning that all sides are equal. So because the molecules of the gas move randomly in a zigzag fashion, it means the molecule or the motion of each molecule can be resolved in three directions, in three dimensions: in the x plane, in the y plane, in the y plane, or in the z plane. So this is the y plane. Because the molecules move randomly, they can move in three dimensions. So the motion of each molecule could be resolved into three planes. It can move in the x, it can move in the z, it can move in the y. So we are going to consider initially just one molecule which is moving towards, say, this wall. I will call this is wall X. It is coming from this wall which I've called wall Y. We are considering just one molecule. Remember, each molecule has a mass m. But in this cubical container, there is a large number of molecules, n, meaning the number of molecules. So we are going to think of the x component of speed. I will call it u1. So I will say the x component of speed will be equal to u1. When I write ux, it means the x component of speed. I will call it u1 for this particular molecule. So the molecule is moving towards wall y. It is leaving, towards wall x, it is leaving wall y. Note that the molecule, when it collides with the wall x, it will eventually reverse the direction of its momentum after colliding with the wall. Remember, we have said the motion is perfectly elastic from the first assumption that the molecules behave as hard, identical, perfectly elastic particles. So, since the collision is perfectly elastic, we are going to assume that this molecule, when it reaches wall X, it will actually rebound. If it rebounds, then it will change direction and move in the opposite direction. Here it had the momentum m times u1 because the x component of the speed was u1. If the collision is perfectly elastic, then it will rebound, the momentum will be m u1 in the opposite direction. The negative is showing that now the momentum is in the opposite direction. So initial momentum, remember, is m u1. After colliding, the momentum p2 is going to be negative m u1 because the collision is perfectly elastic. I want to use this place up profitably. So what has been the change in the momentum? In the x direction, the x component of momentum, which I will simply call px, has experienced a change. And the change in the x component of momentum, delta px, is going to be equal to m u1 minus negative m u1. And this change in momentum in the x direction is actually twice m u1. So for a single molecule moving in the x direction, that is from wall y to wall x, when it collides with wall x, it experiences a change in momentum as it rebounds. Remember, the collision is considered to be perfectly elastic. So it has moved from wall y to wall x. That means it has moved through a distance L. Let's assume that the molecule now has to travel back to wall y after rebounding. That means the time for the next collision can be estimated. The time between leaving wall y until it collides again with wall y can now be estimated. Because it travels a distance which is twice L, that is moving from wall y to wall x and back to wall y after rebounding, then the time of this travel, or the time for the round trip, delta t, is going to be the distance which is twice L divided by the speed which has not changed, that is u1. Remember, this is only in the x direction. So it means I can now find the rate of change of momentum. Remember, by Newton's second law, the rate of change of momentum is the force. That is, we know that force is equal to the rate of change of momentum. So I am going to find the rate of change of momentum, which will be the force exerted by this molecule on this wall. So we are now having that the change in momentum, which is therefore going to be the force, the change in momentum, which is therefore going to be the force. So the force exerted on the wall X is going to be twice mu1, which is the change in momentum, divided by time, which time is twice L divided by u1. And when you simplify this, the force exerted by the molecule on the wall X is going to be actual. I'm simplifying this expression. U1 goes up, the 2 was cancelled. So it becomes m u1, but this should be now squared divided by L. So this is the force exerted on wall X. This is the force exerted on wall X. I may even call it force Fx. The force exerted on wall X. What is the pressure? What is the pressure exerted on wall X? By definition, pressure is the force acting normally per unit area. So the pressure is going to be actually the force over area. And when we simplify, or when we add, the quantities in this expression, the force, remember the area, the cross-sectional area of wall X is L times L, which is L squared. So the pressure is going to be the force, which is m u1 squared over L divided by the cross-sectional area, which is L squared. When you simplify this, I think this gives you m u1 squared over L cubed. Do not forget we are trying to derive this expression, the relationship between pressure and the speed, c. So pressure is now equal to mu1 squared over L cubed. But you and me know that L cubed is actually volume. Also note, we are only considering the x component of speed, yet the molecules move randomly, so they can move in 3 dimensions. They can move in any direction. But we have only considered one direction for now. So, since we have considered one molecule moving in the x, now let's consider any molecules moving in the x, because remember we considered a large number of molecules so that an average behavior can always be considered. So let's say the x components for any molecules, let's say for any molecules, because we have any molecules, for any molecules, let the x components of velocity or of speed be, of course, for the first molecule we have seen u1. Let's say for the second molecule it can be u2. For the third molecule it can be u3 until we reach all the molecules, that is until we reach un. For n molecules, let the x components of speed be u1, u2, u3 until we reach the nth molecule. But remember, for one molecule, the pressure exerted in the x is that. That means for each molecule, the pressure exerted by each molecule in the x direction will have a similar expression. So the pressure exerted by a molecule whose x component is u2 will simply be m u2 squared over L cubed. The pressure exerted by a molecule whose component in the x is u3 will be m u3 squared over L cubed. That means the total pressure exerted in the x direction or on the wall X by all any molecules will therefore be pressure is going to be equal to m over L cubed. I'm writing L3 instead of L cubed. So pressure equals to m over L cubed into brackets, this will be u1 squared plus u2 squared plus until we reach un squared. So this will be the total pressure exerted on wall X by all n molecules. But remember, we consider a large number of molecules so that an average behavior is considered. So let's try to find the average speed of all these molecules. So the average speed of all these molecules, we shall have u1 squared plus u2 squared plus u3 squared plus until we reach un squared. Because we are looking for the average, this will be divided by the number of of molecules. This will be the average speed. But remember, these are squared. So this will be the average square speed. Therefore, this will be, I will simply call the mean speed, the average speed in the x direction, I'll simply call it u. So this will be u squared to be mean square speed, where u is referring to resultant speed in the x direction. So we have that u1 squared plus u2 squared until we reach un squared over the number of molecules, that is the average. We are getting the average square of these speeds. And when you simply change this, you notice that u or n times mean square speed in the x direction is equal to u1 squared plus u2 squared plus u3 squared plus until you reach un squared. So where there is this quantity, I'm going to replace it with this. So the pressure of this gas, of the pressure of these molecules becomes m over L cubed times the number of molecules times the average square speed of the molecules. The average square speed of the molecules. Remember from where we started, I said we consider a large number of molecules so that an average behavior is always considered. Therefore, we are coming up with a simple expression which I want to carry to the next page. We are coming up with a simple expression that I'm going to carry to the next page. So we have come to a simple conclusion from the previous page that the pressure, remember this was only in one direction. We saw that pressure P is equal to m, that was mass of one molecule, times n, which was the number of molecules, divided by L cubed, which we are going to say as the volume, average, the average square speed in the x direction. So I'll call this one my first equation. Now, remember the molecules move randomly in 3 dimensions, and this was only in one direction. So let us assume that the resultant speed of a molecule whose x, y, and z components of velocity are u, v, and w respectively is c. If we have 3 dimensions, those who remember, I want to remind you mathematics. If we have something in 3 dimensions, let me have a simple cube here again. Let's have a cube in 3 dimensions here. We want to find a resultant in 3 dimensions. What is the resultant in 3 dimensions? So we have considered a molecule moving initially in one direction, that is in the x direction. And we now want to find the resultant in 3 dimensions. So first of all, the resultant of these two is this one here. Using Pythagoras theorem, if in the x it is u, in the y it is v, and in the z axis is w. So this was in the x axis, the y axis, and the z axis. In the x it was u, in the y axis it is v, and in the x axis, in the z axis w. First of all, the resultant of these two using Pythagoras theorem, this resultant is going to be v squared plus u squared. That is the resultant of those two, I think, using Pythagoras theorem. But then we want this to be combined with the other one so that we have a resultant in the z. So how shall we find a resultant in the z, including the z? Because now we want something in the z. We want a resultant in the z. So any mathematician will notice that. So any mathematician would notice that, or maybe let me use a simpler axis. Let me delete this first so that I use something simpler for mathematicians to see. So I want to find the resultant of these three, the x, the y, and the z. So I will draw this here. And this can be the resultant of these two vectors, which by using Pythagoras theorem, this will be u squared plus v squared. And then if I want now the resultant, now I have this in the y, the w, and I have this one here. So I want the resultant of these two. So again, I can use Pythagoras theorem because this is, remember, horizontal, perfect horizontal, this is vertical. So they are at 90 degrees. At all cases, they are at 90 degrees. So the resultant of these two can still be obtained using Pythagoras theorem, that is u squared plus v squared plus w squared is equal to the resultant, which I'm calling c squared. So let's say that the resultant of all the components of velocity in the three dimensions or in the three directions is actually c squared. Remember, we have a large number, so that an average is always going to be taken. So taking averages both sides, we have that average of c squared is equal to the average of u squared plus the average of v squared plus the average of w squared. We have taken averages. But because the molecules move randomly in any direction and a large number of molecules exist, and an average behavior has been taken, since the molecules are perfectly identical and they undergo perfectly elastic collisions, then the average behaviors or the average speeds of these molecules will almost be approximately the same. So the average speed in the x direction will be approximately the same as the average speed in the y direction, which will be approximately the same as the average speed in the z direction. And if this is true, it means we can simply say that the average c squared is simply approximately equal to, because these three are equal, I'll just take one of them. So this, since they are three, so this would be 3 times average of u squared. So we have seen that average of c squared, which we are going to call the mean square speed of the molecules, the mean square speed of the molecules is approximately 3 times the mean square speed of the molecules in the x direction only. So we go back to our first equation. This implies, or we can now see, that the average square speed or the mean square speed in the x direction is equal to 1 over 3 the mean square speed in all directions. When I go back and substitute in equation number 1, you notice that pressure will therefore be equal to mn divided by L cubed. Where there is mean square speed in the x direction, I will put there a third mean square speed in all directions. So somehow we are arriving at this expression, as you can see. Maybe you are not, you are very observant. Somehow we are arriving at that equation. So remember, m was the mass of a single molecule and n was the total number of molecules. M was the mass of a single molecule and n was the total number of molecules. So many times you will see this expression written as P being equal to a third m times n divided by, remember, L cubed, that is length, width, height. Since it was a cube, L cubed is volume, so this will be over V, then times the mean square speed in all directions of these molecules. This expression will always be given the list of formula. This expression here is going to always be given the list of formula. But note that m times n, this is going to be the total mass of the gas. M times n is the total mass of the gas, and V is the volume occupied by the gas. V is the volume occupied by the gas. M times n is the total mass of the gas. So total mass of the gas over the volume of the container occupied by the gas gives us the density of the gas. Therefore, rho, which is density, is going to be m times n divided by v. So the expression therefore becomes pressure being equal to a third times density times the mean speed squared, the mean square speed. Pressure is a third times density times, maybe let me write it clearly because I know students will always be students. Square speed, mean square speed. So this is the expression which relates the pressure of a gas to the mean square speed of the molecules that make up the gas. What remains, by the way, is now playing around with this expression here. Note, V is the volume of the container. V is the volume of the container. Note, m is the mass of a single molecule of the gas. N is the number of molecules of the gas. And I want to repeat this. V is volume of the container. M is the mass of a single molecule of the gas, the mass of a molecule of the gas. N is the number of molecules of the gas. And this one here, which is read as mean square speed. This is the mean square speed of the molecules of the gas. Mean or average square speed. The mean square speed of the molecules. It is not the speed of one molecule. It is the mean square speed of the molecules of the gas. So you are going to always be able to play around with this expression in any way you want, as we are going to see later on. So let's continue. This is still very interesting. Let's continue to the next slide. Having seen the relationship between pressure and speed or mean square speed of molecules, remember we said we have to see the equation of state, the kinetic theory of a gas, the pressure of a gas, then the kinetic energy of a gas. So let's see the kinetic energy of the gas. Having derived that expression, let's see the kinetic energy of the gas. The kinetic energy of the gas and the speed of a molecule. Those are the remaining concepts under the kinetic theory of a gas. So let us see. We have already seen from our previous slide, we have seen that the pressure of a gas could be given as a third m n divided by v mean square speed, which could also be given as pressure equals to a third times density times mean square speed. Remember, this is mean square speed of molecules, not of a single molecule. Now we want to derive an expression for the kinetic energy and the speed of a molecule. We know by definition kinetic energy is the energy possessed by a body in motion or due to its velocity. So since we are looking at a large number of molecules, then we shall say that the kinetic energy of the molecules Ek is going to be equal to a half m times times the square speed times c squared, because c is the average speed of a single molecule in all directions. C is the resultant speed of a single molecule in all directions. So this is the kinetic energy of a single molecule. Remember, if you have a large number of molecules, you'll have to multiply this by n to get the total kinetic energy of the molecules which make up the gas. So because we have a large number of molecules, an average behavior is always considered. So the average kinetic energy of a molecule is going to be equal to a half m times the average speed of the molecule in different directions. So from our expression that PV is equal to a third Mn over V, I mean P equals to a third Mn over V times average C squared, we can now come up with very interesting expressions. Number one, I will modify this expression so that it becomes PV equals to a third Mn times average C squared. And when I simplify this any further, I'm going to multiply both sides by, I think I should multiply both sides by 2. I'm going to multiply both sides by 2. I don't know whether that is simpler mathematics. Okay, let me begin by multiplying both sides by a half, so that I bring in an expression for kinetic energy. So this side by a half, I have a half PV. This side by a half, I have a third into a half. I'm multiplying both sides by a half. Remember, this will be a half N average C squared. Just rearranging, I have a half PV is equal to a third. I'm pulling out N because it is not necessary in the brackets. So it is a third into a half M average C squared. Note that this is average kinetic energy of a molecule. This is average kinetic energy of a molecule. So this means I now have that a half times PV is equal to a third N times the average kinetic energy of a molecule. Oh, that is very beautiful. Very, very beautiful. In other words, I am having that PV is equal to 2 divided by 3 times N average of kinetic energy of a molecule. I think that is very beautiful. I want you also to recall that we said the constant K, which was Stefan Boltzmann's constant, was given by R over Avogadro's number. And also remember, we saw that the number of moles was equal to the number of molecules divided by Avogadro's number. These expressions are going to be very important because the examiner will want the expression in any form. Also recall that PV, which was equal to nRT, was also the same as nKT. We saw this earlier on. I will not derive it again. You must be able to relate all these expressions. Let's simply compare PV equals to nKT. Let me use nKT with the expression we just got above, which is PV is equal to 2 over 3 N average kinetic energy. When we compare these two expressions, you notice that this side will be equal. That means we shall simply say that the average, that 2 over 3 N average kinetic energy is going to be equal to N times KT. So N has cancelled out, making average kinetic energy the subject. EK is going to be equal to 3 times KT divided by 2. So many times you will see the expression for kinetic energy or average kinetic energy being given as 3 over 2 times KT. This is the expression for the average kinetic energy of a single molecule. If you have several molecules, of course, you multiply this by the number of molecules. So the average translational kinetic energy of a molecule is therefore directly proportional to temperature. Average kinetic energy of a molecule is directly proportional to temperature. So when somebody talks about absolute zero, I think we should be able to explain what we mean by absolute zero. Temperature is going to be defined as the average kinetic energy of the molecules that make up a system. Because we are seeing that the average kinetic energy of a molecule is directly proportional to the temperature. So it makes sense for us to think of temperature as the average kinetic energy of all the molecules which make up the system. Because if I wanted the average kinetic energy of all the molecules making up the system, I would multiply this by the number of molecules. So, the higher the temperature, the higher the kinetic energy of the molecules. And of course, since kinetic energies are half mv squared or mc squared, the higher the speed of the molecules. So this relationship enables us to obtain an idea of the average speed of the molecules. Let's see the average speed of a given molecule in all directions. So we have that the kinetic energy, average kinetic energy, EK, is equal to a half m average speed squared. Now that kinetic energy is 3 over 2 kT, so I will simply equate this to 3 over 2 kT. So a half has cancelled. It means that the average or the mean square speed is going to be equal to 3 kT divided by the mass m. I'm just making average square speed the subject. So the mean square speed of a molecule is given by that expression. When I find a square root both sides, square root of this both sides, I'm finding the square root both sides, 3 kT divided by m. So it means I remain with average speed without the square being equal to the square root of 3 kT divided by m. So this quantity here, when I find the square root, I'm getting what we call the root mean square speed, which is normally going to be written as RMS speed. Root mean square speed. Sometimes it's going to be written as CRMS to mean root mean square speed. So the quantity, this quantity here is going to be called the root mean square speed of a molecule or of molecules. The root mean square speed of molecules. The root mean square speed of molecules. The root mean square speed of molecules. Actually, this is not that is not exactly equal to the average speed of the molecules, but sometimes it is taken to be so because it's a very important quantity here. After all, we consider a large number of molecules. Therefore, an average behavior is very important. So this quantity here under the square root is called the root mean square speed of molecules. So the root mean square speed is actually proportional to the square root of the temperature, as you can see. It is also inversely proportional to the square root of the mass of a molecule, as you can see. What does this imply? It makes sense that when the temperatures increase, the speed of the molecules also increases. In other words, at high temperature, the speed of the molecules is higher. That's why we say they have higher kinetic energy here. That's number one. Number two, extremely massive particles or extremely massive molecules will have a smaller speed, therefore they have a smaller kinetic energy. Extremely massive particles have a smaller speed. Extremely massive molecules have a smaller speed because we can see that the speed is inversely proportional to the mass, or the mass is inversely proportional to the speed. By the way, taking you back here, this expression here helps us to define what we call absolute zero. Absolute zero. Absolute zero. When somebody talks about absolute zero, for those of you who are much aware of this, this is zero what? 0 Kelvin. Because temperature is directly proportional to the average kinetic energy of the molecules, so when I talk about absolute zero, I'm referring to the temperature at which the average kinetic energy of the molecules is actually zero. At this temperature, the molecules can be considered to be permanently at rest. But it doesn't mean that the internal energy is zero. It may not be zero, but it is minimum. So at absolute zero, the molecules or the atoms have zero kinetic energy. I think that is perhaps the end of ideal gases. All we need is now to come up with a conclusion and maybe do some examples. Conclusion, let's come up with a conclusion. In conclusion, number one, we say the quantity, this is going to be called the root mean square speed or RMS speed of molecules. And I say it is not exactly equal to the average speed of the molecules, but is often taken to be the average speed. It is wrong to think about it as the average speed, but sometimes it is taken to be the average speed. Number two, the root mean square speed is proportional to the square root of the thermodynamic or absolute temperature of the gas. And we have seen it is also inversely proportional to the mass, the square root of the mass of the molecule. So at high temperature, molecules move faster. Large molecules move slower. Less massive molecules move actually faster. Number three, on average, less massive molecules move faster than more massive molecules at a given temperature. That's when temperature is constant. And for a given gas, the higher, this is a typing error, the higher the temperature, the faster the molecules. That is in our conclusion. I think that has been interesting and easy to understand. So we can do a few examples and we wind up this. Examples. Let's see examples. Example number one. So this example is going to help us to understand the difference between mean square speed and mean speed squared and mean square speed or mean root mean square speed, so that we can be able to distinguish these three. There is what we call the mean speed, there is what we call the mean speed squared, and the mean square speed. Those three are different. When you are able to distinguish them, then you are good enough to go. So find the total speed. Here we have five speeds, meaning that there are five molecules. 1, 2, 3, 4, 5. Total speed, here you just press your calculator, you sum up the speeds. Let me pick my calculator. 100 plus 200 plus 300 plus 500 plus 400. I think this doesn't need a calculator. Total is 1500. Total speed, you just add up 1500 meters per second. That is the total speed. Then find their mean speed. Mean, you just add the total divided by the number. So since we have 1500, I will just get 1500 divided by 5. And the mean speed or the average speed is simply 300 meters per second. The mean speed, their mean speed. Of course, in kinematics, average speed of motion is not total speed divided by the number of speeds, of course. But here we are talking about the average speed of the molecules. Then number three, the mean speed squared. The mean speed squared. That means we get the mean that we have already obtained, which is 300, and square it. The mean speed squared. And when we square this, we get 90,000. I think this doesn't need a calculator. This will now be meters squared per second squared. Now, what is interesting is the one we need here in part D. The mean square speed is different from the mean speed squared. The mean square speed means we first need the sum of the mean, the sum of the squares of the speeds. That means for the mean square speed, this will be equal to 100 squared plus 200 squared plus 300 squared plus 400 squared plus 500 squared divided by 5. So this is what we call the mean square speed. It is different from the mean speed squared. Mean speed squared means you first get the mean speed and then square. Mean square speed, you first get the square and then you get the mean. So this, when you press your calculator, summing this up, 100 squared plus 200 squared plus 300 squared plus 400 squared plus 500 squared divided by 5. Okay, so this is giving you 110,000. Still, this will also be meters squared per second squared because each speed is already squared. Then the root mean square speed. Root mean square speed. By the way, you will find that the root mean speed squared will be still 300. But this is the root mean square speed, which will be the square root of this. So the root mean square speed is going to be the square root of 110,000, which will give us 330 meters per second. So notice that the root mean square speed is not actually the same as the mean speed, but sometimes it is taken to be so because you see they are almost close to each other. The mean speed is not the same as the root mean square speed, but sometimes this value is taken to be the same as that value. I hope I've tried to labor much to distinguish between the mean square speed and the mean speed squared. You should know that difference. Number two, example number two. The density of air at standard temperature and pressure is 1.3 kilogram per meter cubed. And the atmospheric pressure is 1.01 times 10 power 5 pascals. Calculate the mean square speed. Calculate the mean square speed. So I told you that the expression PV or P equals to, the expression P equals to a third mn over V average C squared is always given the list of formula. But from this expression, we can also see that pressure is equal to a third times density times C, the mean square speed. They have given us the density, they have given us the pressure, and we want the mean square speed. So we simply substitute. The mean square speed is going to be 3 times the pressure divided by the density, which will be 3 times the pressure, which is 1.01 times 10 power 5, which is approximate atmospheric pressure, divided by the density, which is 1.3. I press my calculator. 3 times 1.01 exponent 5 divided by 1.3. So this is giving me the mean square speed as 2.33 times 10 power 5 meters squared per second squared. That's part A. In part B is telling us to find the root mean square speed, which I will simply write as CRMS, which will be the square root of the mean square speed, which will be simply the square root of 2.33 times 10 power 5. And when I press my calculator to find the root of the answer, this gives me approximately 480, two significant figures, meters per second. Since I've got the square root, then the squares on the units have gone off. Okay, that is example number 2. I hope I have another example, but I don't think so. Number 3. Example number 3. Example number 3, state the meaning of each of the symbols in the equation. State the meaning of each of the symbols in the equation. A half m c squared, or average c squared, equals 3/2 kt. State the meaning of each of the symbols. I think that is an easy question. Do I need to go through it? Maybe, whatever. Okay, so M, we are starting with A. M is mass of the molecule. M is mass of the molecule of the gas. Then K is Boltzmann's constant. That is, okay, this is mass of a molecule of a gas. Then K is Boltzmann's constant. We even saw this in was it astrophysics? Boltzmann's constant or Stefan Boltzmann's constant. And T should be absolute temperature. T should be absolute or thermodynamic temperature. Absolute temperature or thermodynamic temperature. And then with the most important symbol is this one here. Remember, we start with reading this as mean, then square speed of molecules of the gas. The mean square speed of molecules of the gas. The mean square speed of molecules of the gas, that is C. Part B, explain the significance of the quantity a half m mean square speed. Of course, this is average kinetic energy of a molecule. So part B, this one is average a half m mean square speed is the average kinetic energy of a molecule. If there are several molecules, we multiply that by n, capital N, which is the number of molecules. Then use the equation to suggest what is meant by absolute zero of temperature. Absolute zero. We are using now this equation to explain what is meant by absolute zero of temperature. So we know that at absolute zero, that is T equals to 0, since average kinetic energy of a molecule is equal to 3/2 kT, then at T equals to 0, from this expression here, it means the average kinetic energy of a molecule is also 0. So the kinetic energy EK is equal to 0. That means the molecules are at rest. So when someone talks about absolute zero, that is the temperature at which the kinetic energy of the molecules is 0, or the molecules are permanently at rest. The molecules of the gas are permanently at rest. I hope that is clear, home and dry. Example number 3. Example number 3. Example number 3. If not number 4. Example number 3, if not number 4, but I think it should be number 4. Example number 4. The molecules of an ideal gas at thermodynamic temperature T have a root mean square speed Cr. So at temperature T, they have a root mean square speed Cr. Because me, I'm now an expert, I know that Cr is going to be equal to 3 kT over m under square root, because that is root mean square speed is directly proportional to the square root. The gas is heated to a temperature twice T. What is the new root mean square speed of the molecules? So the new temperature is twice T. So I will call the other one, the new root mean square speed, I will call it CRMS. So this will be square root of 3K, where there is temperature, I will put there twice T. divided by m, because the mass of a molecule and the constant K are still constants. So when we simplify this mathematically, this becomes root of 2 multiplied by the square root of 3kt divided by m. That means this becomes root of 2 times the first value of Cr. So the second square root mean square speed, or the second root mean square speed of the molecules will therefore be the square root of 2 times the first root mean square speed of the molecules. That's not a serious question. That is just a simple mathematical question. Example number next, maybe it's number 5, I don't know. Example number 5. The density of argon at a pressure of 1.0 times 10 power 5, that is approximate atmospheric pressure, and at a temperature of 200 Kelvin is 1.6. I hope that is slightly above air. What is the root mean square speed of argon molecules at this temperature? What is the root mean square speed of argon molecules at this temperature? So they have given us pressure, they have given us temperature, and they have given us the density. So I told you must be creative with the expression. Remember I say the expression PV, or the expression P, equals to a third m capital N over V mean square speed is always given a list of formula. I may always forget to give it, that one I know. But since we are given the density and the pressure, we can first of all use those quantities maybe, because we want to find the root mean square speed of argon molecules at this temperature. So pressure is therefore going to be equal to a third times density times the mean square speed. So the mean square speed is going to be 3 times the pressure divided by density. We substitute 3 times 1.00 times 10 power 5 pascals divided by the density, which is 1.6. Pressing the calculator. So we are pressing the calculator, Okay, so this means that the mean square speed of argon molecules is going to be, the mean square speed is 1.888 meters. This is now meters squared per second squared, because it is mean square speed. Then if I want the root mean square speed, which I just wrote as CRMS, the root mean square speed will be now the square root of the mean square speed. That is the square root of the mean square speed, which will be the square root of, oh, by the way, this is times 10 power. There is something I forgot out, I left out here. So the mean square speed, the mean square speed was 1.88 times 10 power 5 meters squared per second squared. So I'm getting the square root of 1.88 times 10 power 5. So when I find the square root of the mean square speed, I get the root mean square speed, which will be square root, which is approximately 430 meters per second to 2 significant figures. So this is the the root mean square speed of argon molecules. I think that is easy. That is very easy. Okay, next we are winding up ideal gases. Next is example number 6. Example number 6. Find the average kinetic energy of a molecule in an ideal gas at a temperature of 500 Kelvin. We want average kinetic energy of a molecule. in an ideal gas at that temperature? This is an easy question. If you are not yet comfortable with the equation of average kinetic energy, you can always derive it. Maybe not to just quote it for people. I know that pressure is equal to a third mn divided by v times the average c squared. I say this equation is always given the list of formula. This means PV is equal to 1 over 3 mn times average of c squared. I multiply both sides by a half. A half, PV is equal to a half. So this will be a third n into a half. M average c squared. Remember, this is average kinetic energy. So it means that the average kinetic energy is going to be equal to, I'm taking this one up, so it will be 3 over 2. It will be 3 over 2 times PV, 3 over 2 times PV over maybe N if you want it like that. But also remember, PV is equal to nRT. PV is equal to nRT. Because I don't have N and I don't have I know R but I don't have N, I may not use this expression. But this is also the same as nKT, you know. So it means I can remove PV and I put nKT. So the average kinetic energy of a molecule is going to be 3 over 2. Where there is PV, I'm putting there nKT divided by N. N has cancelled. So it means the average kinetic energy of a molecule of a gas is given by 3 over 2 times kT. This is not a hard expression. If you're not always sure of it, you can always derive it from what is always given. So let's use this expression very fast to find what we want to find. So we want to find the average kinetic energy of a molecule in an ideal gas at this temperature. So we simply substitute. This will be 3 over 2 times K. Remember, K is Stefan Boltzmann's constant, but K is R over Avogadro's number. So this could also be 3 over 2 times R over Avogadro's number and A, then times the temperature T. However, if you know K, you can also substitute K because K is 1.38. But since I don't want to use K, I know R is 8.314. Avogadro's number is 6.02 times 10 power 23, then times the temperature in Kelvin units, which is 500. Then I press my calculator. So by pressing the calculator, I'm getting 1.04 times 10 power negative 20 joules. You can also press yours and see. So that is the average kinetic energy of the molecules, or a molecule of in an ideal gas at that temperature. Remember, average kinetic energy of a molecule is directly proportional to temperature. Okay, next is number 7, example number 7. Example number 7. Example number 7. I think this is the last example. It could be the last example, maybe. Find the root mean square speed of the molecules in hydrogen gas at 500 degrees Celsius. Find the root mean square speed of molecules in hydrogen gas at 500 degrees Celsius. Remember, temperature must always be in Kelvin units. The temperature here must always be in Kelvin units. So we want the root mean square speed of the molecules in hydrogen gas at this temperature. At least we have already found that the average kinetic energy, I can't repeat deriving this. The average kinetic energy of a molecule is equal to 3 over 2 times K times T. Remember, this is small k. But remember, average kinetic energy is a half m average c squared. So it means a half m average of c squared is going to be equal to 3 over 2 kt. So we want C actually. We want C because it's what we are going to use to find the root mean square speed. So it means the mean square speed C is going to be equal to 3 kt divided by m. That is the mean square speed. And if I want the root mean square speed, I will actually find the square root. I'll find the square root of 3 kt over m. But I want you to note that we want the root mean square speed of molecules in hydrogen gas. They have given us the relative molecular mass of hydrogen to be 2. That means we need actually the total kinetic energy of all the molecules. So I will have to multiply this by the number of molecules. Note that if the relative molecular mass of hydrogen is 2, that means 1 mole of hydrogen is 2 grams, which contains 6.02 times 10 power 23 molecules. 6.02 times 10 power 23 molecules. So let me try to find the mass of just one molecule. So the mass of one molecule, m, because m is the mass of one molecule. The mass of just one molecule is going to be, remember mass is, we say the mass over molar mass is equal to the number of particles over Avogadro's number. So the mass of one molecule is going to be the number of molecules, which is actually the number of molecules, which is actually 6.02 times 10 power. How should I do this? Okay, so let me simplify this. Let me just do it like this for students to easily understand it. We want the mass of just one molecule. We want the mass of one molecule, but 2 grams contains 6.02. So hydrogen 2, that means 2 grams contains 6.02 times 10 power 23 molecules. That is Avogadro's number. So one molecule should have a mass of 2 grams divided by 6.02 times 10 power 23 molecules. That is just for one molecule. If you want to change it to kilograms, you multiply this by 10 power negative 3. So I'm now just going to substitute here to find the root mean square speed. So this would be 3 times k. K is 1.38 times 10 power negative 23 without a problem. Then times absolute temperature should be in Kelvin units, that is 500 plus 273 Kelvin, divided by the mass. The mass should be in kilograms, so it will be 2 times 10 power negative 3 divided by 6.02 times 10 power 23. But this should be under the square root, because we are finding the root mean square speed of these molecules. So let's press our calculator very fast. 3 times 1.38 times exponent negative 23 times this is 773. So 6.02 times 10 power 23 goes up, divide by 2 exponent negative 3 under square root. Okay, so to only two significant figures, I am getting 3100 meters per second as the root mean square speed of the molecules in hydrogen gas. You can also check through, you can try to find that value and see if it is the same. Okay, well, this comes to the end of ideal gases, so we qualify for a simple self-check. If you have been watching this lesson, you should be able to attempt the following self-check. An ideal gas has volume 0.5 meters cubed at a pressure of that and a temperature of 17 degrees Celsius. So we're going to calculate the number of moles, the number of molecules. The answers are even given. We're just trying to show the working and verify. Each molecule may be considered to be a sphere of this radius. Calculate the volume of one molecule and the volume of all the molecules. In addition to this, you're going to find the kinetic energy. Find the kinetic energy of of a molecule of this gas. Find the kinetic energy of the molecule of a gas at a temperature of 273 Kelvin. Find the kinetic energy of or the average kinetic energy of a molecule of an ideal gas at a temperature of 273 Kelvin. Part D, write STP in full. STP in full and give corresponding values and state corresponding values. So write STP in full and give corresponding values to each quantity. That is question part 2. That is part D. I think that exercise will be enough for now. I hope you have enjoyed this. Thank you for watching this lesson, and we shall meet in the next lesson. For now, have a good day. Bye bye.